welcome to Algebra 2 with Mr. Clausen. Today I want to talk to you about roots and radical expressions a little bit. And specifically what I want to go over is look at structures of radical expressions. We'll look a little bit at how to find roots and use the prime factorization technique for finding roots of rational expressions, and then finish up by looking at some simple radical expressions and how to simplify them. So without further ado, I want to talk a little bit about radical expressions, what they are, and how we can analyze them. So for example, if we take the square root of 9, all of you have probably seen this before, understand that 9 is a perfect square and that this is equal to 3. What you may not know is that this is actually a inverse operation to the power function. So if we say, for example, a to the nth power is equal to b, the opposite operation to a square root function would just be saying that, hey, if you have 3 squared, that is equal to 9. Okay, so whenever we're looking at this, the inverse operation for a of nth power equals b would just simply be the idea that the nth root of b, which can also be viewed as b to the 1 over nth power, is equal to a. Okay, and what you have seen before is you've seen a radical sign before. This is just what we use to indicate this type of behavior that we're trying to describe. The part on the inside here we refer to as the radicand. But the new part that I want to spend a little bit of time talking about today is this n value, and this is your index. And everything that you've dealt with to this point in Algebra 1 or your previous math classes has been n to the second root. Okay, and all this is saying is that we are looking for the square root. We're trying to split it up. If we say, for example, 3 to the second power, just like I have here, this is really saying the same thing as the square root of 3 times the square root of 3, which would equal the square root of 9, which is just equal to 3. Okay, and if there is no index identified, we always assume that it is equal to 2. And because of this idea that you have to square these values, we always know that the value has to be positive, which is why negative square roots are not possible. Okay, but if we're looking at, you know, something with a higher root power, let's say, you know, the cube root of 125. Okay, and the idea here is, you know, if you have some value a to the third power equal to 125, well, hey, what is a? Well, normally what you would do if this was a square is you take the square root of it. Well, we can do the same thing. We can take the cube root of it. We can take the cube root of the other side and find what a equals. And just simply break down and say, hey, a is equal to 5 in this given circumstance. So 5 cubed is equal to 125. And we can actually solve these out and look at these different values and expand on, you know, how to find these roots in these different situations. So with that said, I want to go and I want to show you some examples of finding roots using what is typically called the prime factorization technique. So an example of this might be, you know, if we have the square root of 64, you've probably seen this before. If you have the square root of 64, some of you might see this and go, oh, I know the answer to this. And if you want to find this and you're not sure what it is, or you don't use your calculator, we can just simply go 2 times 32, and we can do the process of finding all the factors of a given number, and we break it down to all its individual prime values. And what I'm going to point out here is that with the square root of 64, I have 6 2's. So what this means is that if I take the square root of 2 to the 6th power, I now have this large number broken down to all of its prime to a given power. And what this allows me to do is it does a couple things. So one example might be is if I look at this, I can simply go, hey, I have 6 2s. This means 2 times 2 times 2 times 2 times 2 times 2. And I can now look at this and go, well, there's 3 pairs of 2s. Okay, so there's 3 pairs of 2s here, so I can pull out a 2. There's 3 pairs of 2s here, so I can pull out a second 2. And there's 3 pairs of 2s here, so I can pull out a third 2. And thus, this would equal 2 times 2 times 2, or 2 to the third power, which is equal to 8. And I would know that the square root of 64 is equal to 8. Okay, and when we're looking at this, this can be a really quick way to split apart and find some of these given values. Another way that we can do this is that if we understand this is 2 to the 6th power and this is all we have, well, we can just go 2 to the 6th power, the square root of 2 to the 6th power, and just say, well, we understand that the nth root of b is equal b to the 1 over n power. So if that's the case in this circumstance, you know, b being 2 to the 6th power and 2 being the index, we can say that the square root of 2 to the 6th is equal to 2 to the 6th, and in parentheses, the 1/2 power. And one of the things that I will tell you is that whenever you have a power multiplied by a power, you just simply multiply these values, and you can say 2 to the 6th power times 1 over 2. And this would equal your 2 to the 3rd power and get you the 8 again that you had before. So just a kind of a tidbit of information to keep in mind there. We'll talk about that more in detail in the 3rd or 4th video in this sequence. So let's break this down a little bit more. So let's say, you know, I want to take the cube root of 64. So if we have the cube root of 64, one of the things I want to talk about here is that now we have a situation where we're talking about the 1/3 root, or we need 3 2's in order to pull out that value. So again, 2 times 2 times 2 times 2 times 2 times 2, the same type of situation. So the only difference with a cube root instead of a square root is that we need 3 of these 2's to pull it out of the rat of sand, and then say 2 square roots of 2 times 2 times 2, or I should say cube root. And since we have 3 more 2's here, we can pull this out and say 2 squared, which is equal to 4. So the cube root of 64 would be 4. And again, the same situation could apply here, where if you go 2 to the 6th power to the 3rd root, we can just simply go 6 and divide it by the 3 and know that 2 squared is what gets pulled out, and that equals 4. So you can do that as well. And we can keep expanding this into a situation where we can say, let's say the 6th root of 64. And if you have the 6th root of 64, we can simply just say 2 to the square root of 6. 6 over 6 is 1. So the 6th root of 64 is simply equal to 2, because you need 6 2's, 2, 3, 4, 5, 6 2's. You need to pull all 6 of those 2's out to find that root and to get that specific value. Okay, so this is how we find roots. This is the prime factorization method, where you can take a larger number and split it to all of its individual primes and find some of these roots. So let's look at a couple examples on how we can simplify radical expressions so that you can apply this context. So again, the same situation here is if I'm looking at a square root value like 16 and x squared, the only difference here is now that we have a variable present, is we just have to split these two pieces apart. And if it's easier for you, you can split it into 16 and x squared and take the square root of those. And if you notice that 16 has 2 4's and x squared has 2 x's, you know, another way it could be written as 4 squared times x squared, and this will give you 4 times x. And you know that your solution for this would be 4x. That would be a simple way that you can simplify this radical expression. And the same thing's going to occur here. So with 27, what I'll tell you is that is a perfect cube. And if you don't see it, all I'm going to say is just prime factor it. Factor out all the primes. And what I'm going to point out here is that you have 3 3's. Okay, so we can go the cube root of 3 to the third power, which is equal to 27. And we can also say the third power of y over 6. So just like with the 2's that I was talking about in the previous example, if we go y to the 6th power and take that 6 and divide it with that 3, we know that there will be 3 y squareds that make up y to the 6th power. And that if we pull all 3 of these out, we can pull this in front of the radical sign. So in this specific case, 3y squared would be the simplified radical expression here. Again, just looking at some other examples so that you can see how we apply this. Another situation would be as if, let's say we have a 5th root. Okay, so again, I'm going to prime factorize this. 2 to 16, 2 to 8, 2 to 4, 2 to 2. I have 5 2's, which works out really nicely. So the square root of 32 is 2 to the 5th power, or the 5th root of 2 to the 5th power. And if we want to multiply that, one of the things that we can do is we can take the 5th root. Y to the 10th power would be the same thing as y to the 2nd power taken to the 5th power. Okay? So again, because you need 5y squareds pulled out simultaneously in order to get this factored out, that's what you have to do. So if you go y squared 5 times, that'll get you y to the 10th power, and then we can pull out the y squared. We can pull 2 to the 5th power, and we would get 2y squared as our solution. Now the last example I want to show you is kind of a unique one, and the reason I want to show you this is I want to bring to a little bit the relevance where I was talking about if you go y to the 10th power and you multiply it by 1 over 5, that's how you get y squared. The same thing can apply here. If you go x to the 6nth power and you multiply it by 1 over 2n, this will cancel out the 2 and the n, give you 3, and you'll get x to the 3rd power as your final solution. So with that said, I hope this expands your ability to simplify some of these radical expressions and that you have a little bit more clarity about how to dissect some of these. And with that said, let's do math.